We're going to skip this and go right to and highlight the first thing that we looked at, which was adding functions. And it says if you add functions, all you do is add the y values. Okay? Some notation stuff. This is important. We write adding functions f and g. This is the nice notation, which says f of x plus g of x. This is the not as nice notation, which the exam seems to like to use lots, just to see if you know it. F of x plus g of x is the same as f plus g of x. So personally, what I like to do is every time I see f plus g of x, I like to rewrite it as f of x plus g of x, because this makes sense. To me, it makes more sense. And in an equation, what's the f of x? That's your y value. Does it make sense that this is just telling you to add y values? So f of x plus g of x is just saying add the y values. For example, if we had, and here's a good example of what the textbook will do, or the exam will do, they'll say, what's f of x, f plus g of 2? The first thing you'll do if you see this notation is you will change it to the notation you're used to. This means f of 2 plus g of 2. And f of 2 is asking you, what's the y value when x is 2 on the function f? The function f is the red one. What's the y value when x is 2? It's 2. What's the y value when x is 2 on the g function? That's the blue graph. It's -1. If I added those together, I would get 1. So adding this function from this function means I should have the point 2, 1. What we can do when we're adding our functions is just try to add as many nice points as possible. Right? Can you see that here the y value is 0? Here the y value is 3. What's 0 plus 3? On the green function we'd have -2, 3. Are there any other nice points you could add? Maybe this one and this one. What's 1 plus 2? 3. So the textbook goes through, it adds a bunch of them, puts those points in. Now, the domain of the green function will be greater than -2, because when adding functions, you can only add things if both of them have y values. And since the red function is only defined when x is bigger than or equal to 2, -2, sorry, then the green function is only defined when x is bigger than or equal to -2. That's adding functions. Subtracting functions. Again, we'll take out our highlighter. We've got the nice notation and the not nice notation. Again, whenever you see the not nice notation, change it back into the nice notation. And now we're just subtracting y values. So for example, if you had 2 minus a -1, you're going to get 3. And doing a bunch of nice points, right? Here you would have 0 minus 3. And sure enough, we have the point -2, -3. Get enough points until you feel comfortable with what you think the shape looks like, and you can draw the graph. Again, since the domain of the red graph is bigger than or equal to -2, when we subtract, our new function also will have that restricted domain. And finally, multiplying, same idea. Oh, this one, they have so much fun with bad notation. Here we go. So first of all, multiplying functions. There's the regular notation. There's the not nice notation number 1. Sometimes I've seen it like this. Can you find out f times g of 2? Okay, if you see this not nice notation, change it right away. This is f of 2 times g of 2. F of 2, that's my red function. It's equal to 2, the y value. G of 2, that's my green function, or blue function, sorry. It's equal to -1. If I multiplied those together, I would get -2. And sure enough, why can't they just pick the one notation that's easy and stick with that? I don't know. Notations, different ways of writing things, you're going to use lots. This particular notation, maybe if you take some university courses, depending on the textbook, might have different notations. Again, same thing with the domain. The domain is restricted, so then the new graph's domain is also restricted. And they've summarized that here at the bottom. These graphs illustrated when you add, subtract, or multiply, the new function has the same restrictions on the domains as the functions you're working with. So if we look at example 1, you've got f of x plus 2 and g of x. So what we're going to do is we're going to graph both of those on their own. I'm going to graph one in blue and one in red. And when we add, subtract, or multiply these, I'm going to draw the new graph in green. X plus 2, that's my blue graph. It has a y-intercept of 2, a slope of 1. There's my blue graph. And my absolute value graph from transformations looks like that. State the domain and range. So for my red graph, domain is everything. Range is bigger than or equal to 0. For my blue graph, the domain is everything. The range is everything. Given h of x, which we will do in green, is f of x plus g of x. Write an explicit equation for h of x. So there's terminology right there. We'll highlight that word because if we do not know what explicit equation means, we are not going to be able to do this question at all. So first of all, what is an explicit equation? An explicit equation, well, it's an equation, so we'll have yellow, no. H of x equals, because it's an equation, and an explicit equation means that you will only have x values on the right-hand side. Right now, h of x equals f of x plus g of x. That's in function notation. That's not an explicit equation. Explicit equation, maybe you want to write here, in terms of x. So f of x, which is x plus 2, plus g of x, which is the absolute value of x. And what does x plus 2 plus the absolute value of x look like? Because we're going to want to determine its domain and range. Well, if I'm adding functions, I can just pick some nice values. Can you see that 0 plus 2 would equal 2? 1 plus 1 would equal 2. 0 plus 2 would equal 2. Here I would have 1 plus 3, it would equal 4. Here I would have 2 plus 4, which would equal 6. And if I kept doing values, I would get the following graph. And if I wanted to find my domain and range, since I've graphed it, I can still see my domain is everything. And I can now see that my range, y is bigger than or equal to 2. Now, just for fun, I'm going to show you how you can tell that that's what the graph is going to be algebraically. Okay? Can you see that the green graph sort of has two parts? It has one part that's a straight line. Would you agree that this straight line looks to be the equation y equals 2? And the other part, which is another straight line, which has a steeper slope, it has a slope of 2 and a y-intercept of 2. I'm going to tell you that that line's equation is 2x plus 2. Now, when x is bigger than or equal to 0, would you agree that the absolute value of x is the same as x? Oh, thank you, Nico. And if the absolute value of x is equal to x, then h of x is the same as x plus 2 plus x and we get 2x plus 2. When x is less than 0, does it make sense that the absolute value of x is the same as negative x? Like if x is not negative 5, absolute value of negative 5 is positive 5. I can make negative 5 equal to positive 5 by multiplying it by a negative in front. Negative 5 would make it positive 5. So whenever our x values are less than 0, the absolute value of x is going to be equal to negative x. That would make our equation for h of x when x is less than 0 be x plus 2 plus a negative x, which simplifies to just be 2. And so through an algebraic analysis of this, I could also see these two graphs. As you get into calculus and in university, you could now have a different way of writing the explicit equation for h of x. H of x has two equations. One equation is 2x plus 2, and that is true when x is bigger than or equal to 0. And the other equation is just 2, and that's true when x is less than 0. For functions, this is called piecewise notation because your function has two pieces. There's no equation that nicely represents it all together. Sometimes we have to write it in 2 different pieces or 3 different pieces. In this case, we have 2 straight lines. This is the equation of one of the lines. This is the equation of the other one. Okay? Everybody good? I'm going to erase this. Yes? because I want to have, for part C, nice. For part C, which I'll do in purple, we'll make P of x, f of x times g of x. So again, we talked earlier about what are some easy things to multiply. When either of the functions is 0, it's going to equal 0. When one of the functions is 1, what's 1 times 1? 1. What's 1 times 3? 3. Take another couple points if you'd like. For example, on the blue graph here, I would have -1, and on my red graph, I'd have +3. 1 times a -1 times 3 would be -3. And so what we get, it appears, looks like this. Now, again, we could do more points to get a better accurate of it. Kind of looks like an x cubed graph. Okay? It won't be an x cubed graph in the end. But based on our graph, we could say that the domain is everything and our range is everything. If I want to really analyze what this question is doing, I could look at the algebra. Right? Again, when x is bigger than or equal to 0. Oh, we haven't done the explicit equation yet. Sorry. The explicit equation for P of x would look like f of x is x plus 2 times g of x, which is the absolute value of x. Again, we're going to look at the algebraic representation of this. This is a little bit difficult to understand in this notation, because what does a graph of x plus 2 times the absolute value of x look like? Even though we've drawn it out there to get an idea, we can analyze this. We can say, well, when the absolute value of, when x is bigger than or equal to 0, the absolute value of x is just the same as x. So in that case, my P of x would equal x plus 2 times x. Can you see that that's a parabola with x-intercepts at -2 and at 0, because it's in factored form? And when x is less than 0, the absolute value of x is equal to -x, so P of x would equal x plus 2 times the -x. Once again, it has the same x-intercepts, but can you see that this parabola would be opening down? If I had this one is a parabola that opens up, has x-intercepts at -2 and 0. Parabola that opens up, I'm going to just draw it in a dotted line, would look like this. And this graph would also have x-intercepts at -2 and 0. But when you multiply it out, you get a -x squared. And that parabola would open down. And our function P of x, in the end, in piecewise notation, has two pieces. It says it would equal x plus 2 times x when x is bigger than or equal to 0. And it would equal x plus 2 times the -x when x is less than 0. So when I think about those two parabolas, for my final graph, I'm only going to choose the x plus 2 times x when x is bigger than 0. So I pick the green graph only when x is bigger than 0. And I pick the blue graph when x is less than 0. And so in fact, it's not an x cubed graph. We have a really sharp point right there instead of a nice smooth curve. And this is the algebraic way to understand where both of those parts come from. Okay, questions for practice are 3, 5, and 10.